Hi everyone, this is an extra lecture that I promised because we had some time loss due to the class being cut a little bit short first couple of class times, so I wanted to give you this lecture on wave mechanics. This is material that you likely covered in your undergraduate courses, but it's good to review, and I thought that I would do this video so that you can watch it and do this review material, and then we can move on to more advanced topics in the actual lectures. So the topic of this is wave mechanics, and we're going to look at basically the motion of particles in some potential. And as usual, we want to set up our quantum mechanical space, which for wave mechanics is L2. It's the space of square integrable functions, and we will mostly look at one-dimensional problems. So this is the motion of a single particle along a line. And in general, you know that you have position and momentum operators, and you saw in the guest lecture how these operators behave. And we know that if you act with a position operator on a wave function, it's a function of x, then this becomes x by x, and we know that p acting on a wave function is a function of x, and that's minus IH bar times the derivative of phi. So those are the important properties, and remember that we have this notion that operators acting on infinite dimensional spaces like L2, they can have continuous spectra, and these two operators are sort of examples of that. And you could, in principle, identify kets with eigenfunctions of these operators. In particular, this would be the eigenfunction associated with position. And so there's a kind of mapping between kets like this, and of course, remember this is space of functions, so what kind of function would correspond to this kind of eigenket? It would just be the delta function, which is a function of some other variable I might call x prime, and it's zero everywhere except for where x prime is equal to x. And this is a function, it's not square integrable, but we can make this association. And so often what physicists do is use objects like this and our usual kets, which have a correspondence with the function, say, the function that corresponds to an element of this L2R. And so you have this mapping, and in some sense you could also identify the following object. So what's this thing? This would be an inner product between two of these elements, which we're going to treat as elements of our L2R space. Well, how would you do this? You know that an inner product between two functions in principle is the complex conjugate of this function. Well, that's just going to be this. Its delta function is a real function, and you integrate it against your function that's an element of that space, and you just get back out the function evaluated at x. So we're going to kind of use this mapping to associate inner products like this with the function itself. And this is sort of what you have to keep in mind is going on in the background mathematically. That these are not actual elements of our space, but we can use them as such as long as we kind of make this association between the element and the Dirac delta function, because we know that, incidentally, you can sort of do the same thing here, right? You can, if you treat these as delta functions, what's this thing? Well, this is the inner product between two delta functions. So what do we do here? We would put delta x minus x double prime is the variable of integration. And then here you would have x prime minus x double prime, and you integrate over dx double prime. This means that this is vanishing everywhere except where x double prime is equal to x, so this becomes just what you'd expect, x minus x prime. And that's what you wanted all along for, if you remember, this is supposed to be the inner product of these basis vectors. But they're not really basis vectors, again, because they're not an element in our space. So we're going to use this frequently to understand what's going on for one-dimensional motion. Incidentally, you also have then the probability of observing a particle on some interval between A and B. So this is probability observing a particle in an interval between A and B. That's just going to be the integral from A to B of dx phi of x. So that's pretty much it for the position space sort of manipulations. It's often convenient to go to momentum representation. And you should have seen a little bit of that from the guest lecture. These are going to be pseudo-eigenvalues, vectors rather, of the momentum operator. So just like x is a pseudo-eigenvector of position, you could in principle also have pseudo-eigenvectors of momentum. And then you can ask, what's the wave function associated with that? And you can just figure out what that is. It's the following. So if this is an eigenvector of momentum, then this becomes p x p, and this would be the wave function associated with, so it'd be whichever element of, pseudo vector that's a function but not an element of L2 that's associated with an eigenvalue of p for the momentum. So this is some function, which we call chi of p, as a function of x, and then it has to be equal to minus I h bar dx, chi of px. So you can solve this as a simple differential equation. The solution is an exponential. So chi of p of x has to be equal to 1 over square root of 2 pi h bar x over h bar. And why do we choose this normalization? It's to ensure that you have orthonormality, that p dotted into p prime is this. So what is that? By the way, now you can do this kind of thing by inserting a completeness relation. We can integrate over some dx, like this. And now we can stick in these guys in here, and what do we get? It's 1 over 2 pi h bar, negative infinity to infinity of dx e to the I over h bar p minus p prime X. And so let's see, where did this come from? Again, so X, so I must have missed a minus sign, so this is P prime minus P. Like that, so this part is the complex conjugate of the reversed guy, and we know that, so this rather is the complex conjugate of X dotted into P, and that's by definition this chi function, and this is the solution to this differential equation, and again, this normalization is chosen so that this works out. How does this work out? It's the complex conjugate of this function, so it becomes 1 over square root of 2 pi h bar times e to the minus I over h bar p, that's this part. And then this part is just p prime, so it's just chi of p prime there, so that's this term. And you can do this integration gives you a delta function in p. It gives you back p prime minus p, just as we wanted. This is even, so we could, it's the same as p minus p prime. So that's what it is. This is a solution to this differential equation, and you see if we choose this normalization appropriately, we can get this orthonormality condition. So these functions are the analogs, so this is like the p pseudo-eigenvector. You see you have the p's, which are these guys, and you have the x's, which are these guys. Both of these functions are not an element of L2R because they're not square integrable. If you square this and try to integrate it, you get some crazy oscillating function. It doesn't give you anything sensible. But you can still associate these. These are called, again, pseudo-eigenvectors. Associate them with a continuous portion of the spectrum. In this case, a continuous momentum that you can have. And in this case, these x's are pseudo-eigenvectors associated with the position of the particle. And, of course, these two things are related to each other via a Fourier transform. So, in particular, the wave function associated now. So again, if you look at this chi there, you see that chi you can treat as a function of either x or p. So in principle, you could, just as there is a space associated, so there's a space associated with the x coordinate, and it's the space of wave functions is a function of x, the position where your particle is. And we know what those are. Those are the wave functions. But similarly, there's an equivalent description where you have wave functions as a function of the momentum of the particle. And that's also a space of square integrable functions, but it's functions of p. And these two spaces, they're related to each other. You can get from one to the other by Fourier transforming. So that's something useful to know. And so this x, whenever we dot x into a ket like this, x dot phi, that's the wave function. So we know that. X dot phi. But similarly, you can take the p ket and dot it into phi, and that gives you something as a function of p. It's completely analogous. So now you can figure out how this is related to this guy by sticking in a completeness relation, if you want. And if you did that, you would get 1 over square root of 2 pi h bar integral negative infinity to infinity dx. That's from that completeness, sticking in the x ket bra thing. You get e to the minus ipx over h bar, phi of x. And here you get you can do the same thing. You can stick in a completeness relation for P. Is that remember that you have completeness for both operators, right? These are observables, they're Hermitian operators, X and P. So they can have that Hilbert space decomposition theorem. And we know that the spectrum of both of this is just continuous. X can go from minus infinity to infinity. P can go from minus infinity to infinity. So there's, just as there is for X, there's a completeness relation for P. And so we could stick that into here and compute sort of the inverse Fourier transform, which is 1 over square root of 2 pi h bar minus infinity to infinity P inverse. Remember, this is not inverse px over h bar phi of P. And I like to put a tilde there just to remind you that the tilde guys live in this space, the LPR. The regular guys, a function of X, live in this space, and they're related to each other just via Fourier transforms. So this is very important, sort of the basis for wave mechanics. Again, the idea is you can jump back and forth between the two different spaces. Why can we do that? Because we know our Hilbert space has a decomposition theorem associated with either the position or the momentum operator. We can either have this completeness relation or the one for X. So there's an equivalent one for X. And we also know the inner product between X and P. That's just these Fourier coefficients. And that basically gives you the formalism associated with wave functions in either the position or momentum space. And so what we're going to do now is look at various solutions to the Schrödinger equation using this kind of formalism. So we're going to move to the Schrödinger equation. So what's the Schrödinger equation? We'll show in class a bit later that the most general form of the evolution operator for time evolution for these spaces of one-dimensional motion, they're given by the following form. There's a kinetic energy piece and a momentum. There's a kinetic energy and a potential energy. So kinetic, potential, and we know what these things are. I'll show you later. This is really the most general form. You could derive this just by arguing that you have a one-dimensional motion, particle in one dimension, and that your system has to be invariant under Galilean transformations. But we'll see that later. It's not so important now. The point is that this is very general. Any particle motion in one dimension will have a kinetic energy and a potential energy. That sort of should be physically intuitive. And then we know that unitary evolution of any state is just given by the Schrödinger equation. And so now we can figure out what this does. We can stick this h into here and figure out what h does. So how do we do that? Well, it's easy. We just take x, this cat, and dot it into the psi to get the wave functions. So you get h bar, d psi, dt. Of course, this dotted into this doesn't do anything. These are just constants, and the derivative is just the difference between psi's at adjacent times. So this must be just h bar partial derivative with respect to time of the wave function, which is going to be a function of x and t, because this makes it a function of x, some x, and this we take a derivative with respect to time. So that's that bit right there. And then you also have x, what else? It has p squared over 2m. So let's do the p squared part. The p squared part, what does that do? That we know just takes derivatives of the wave function. So this thing is going to be minus I h bar dx squared. So this is p squared acting twice on psi of x of t. There's I squared, so there's a minus sign that you get, and you get minus h bar squared, two derivatives acting on x of t. So this isn't really squared, this is this operator p, and we're acting twice on the wave function. This gives us this. And of course, this part, the potential, well, thankfully this is written as a function of the x operator, and these are the eigenstates of x, again, pseudo-eigenstates. So we know what that is. That's just going to be v as a function of little x. This is big operator x, this little x, times psi of x of t. So we know this, and that means the Schrödinger equation just reduces to this equation, which you're familiar with probably from undergraduate. It's sort of what a lot of courses start with, is just the Schrödinger equation for a particle moving in one dimension and some potential. There's this piece, I h bar ut, and so on, and then there's two derivatives, and then there's a potential piece. So that's the sort of big important equation that we're going to just look at for a while. We want to solve this thing. I mean, really this is the whole setup, and now this is just a differential equation that we're going to try to solve. Now, partial differential equations are difficult because you have two different variables. For those of you who might know, this is very close to a diffusion equation. If you make a variable transformation from t to I times tau, some other time, imaginary time, then this becomes like a diffusion equation, which maybe we'll talk about later. But we also know that there are special states, right, that are eigenstates of H. And those eigenstates, we know that those are equal to some constant E times psi. And so then this equation becomes really easy to solve because this is just a constant. And so then the psi just evolves with a rotating phase. Remember that then for stationary states, psi is e to the I, e times t over h bar, and so on. So that's what we're going to look at now, is stationary solutions. So we're going to look for stationary solutions, ones that where the time dependence is really easy. It's just gives you e to the I t type of business. So we want to look for solutions where this part, the h psi, this guy, is equal to a constant. So we're going to look for h psi is equal to e psi, the stationary solutions. And of course, then remember for these guys, psi of t is equal to e to the I t over h bar times this constant times psi of 0. It's really easy, right? You can just solve this equation very simply, just exponentials, and you get this rotating phase. But we're going to look at this, and this equation for us has a different form. If we want to write it in terms of functions in L2, so there we have minus h bar squared over 2m, like that, plus v of x. And that has to be equal to e times psi of x. Right? So this is the equation we want to solve. Now this is a ordinary differential equation. We can get rid of this t because we already know how it will evolve in time. There's no t here, there's no derivative with respect to time or anything, so you can just get rid of this t. So I have it there. So we're going to look for solutions to this. This is going to be now our sort of objective. It is to look for, so here this arrow means it's stationary solutions. We're going to look for solutions to this equation. And then we already know how to do the time evolution if we want for the stationary solutions. So we have to solve this thing for various potentials. So that requires us to choose a particular potential. And we'll do that in a moment, but before we do, there's one more concept that's important here, and it's related to this probability of observing a particle. And it's the concept of a probability current. And it'll be important when we try to solve that equation, stationary Schrodinger equation, time-independent Schrodinger equation. So let me just talk a little bit about probability currents. So what's a probability current? We know that the probability density, again, it's this thing, the probability of observing a particle, it's related to the wave function squared. So we know that the probability density, maybe I just write it as rho or something, of x in t. So the probability density associated with observing a particle at position x at time t. So when you integrate over x, you'll get an actual probability like this one. Integrate over some interval, you'll get a probability. And this thing is just the magnitude of your wave function that you find with the Schrodinger equation or what have you squared. So if we look at this, you want to know how this evolves in time. We sort of figured out how psi evolves in time with the Schrodinger equation, but you can just as easily figure out how rho evolves in time. And what's that? Well, that's just a derivative of psi times psi star. Again, this is a function of x and t, it's just shorthand. So you use the chain rule. It's psi star ut psi plus psi star. But we know what these things are because we have the Schrodinger equation. So for this part, that's really just the regular Schrodinger equation. That's h bar squared over two m. Oh, so it's h bar over 2mi. Let me bring back the Schrodinger equation. Okay, so you see here's the Schrodinger equation. We want this partial derivative with respect to t of psi. So we have to divide out by ih bar. So this over here becomes minus h bar over 2mi. Right, and this is psi star. Partial derivative with respect to x of psi. That's this part. And then there's the potential plus v of x over ih bar. Psi star psi. That's the first term. The second term we can just take the complex conjugate of both sides of this equation, and we could put a star here and a minus sign there if we want, and a star here. The potential is real, so nothing happens there. Put a star there. So now we know what this is. This thing is plus h bar over 2mi psi dx squared psi star minus vx over h bar psi star. Well, that's very convenient because these two terms just cancel. And you're left with the following thing. You're left with minus h bar over 2mi, right? And it is these two terms. You can factor out a derivative with respect to x, actually. I'll show you in a moment, but it's just this. We can do this because, look at this, if we expand this out, this is the derivative of this whole thing. It acts on this first guy, and it acts on this guy. So you get this derivative of this guy times this guy minus the derivative of this guy, which is the same, times this. So they cancel, the cross terms cancel. So the only terms that are left over are where this acts on the second guy, which gives us this term. So this term is just this term, and then the other term here, this guy acting on this guy, just gives you this and this. And then the other terms cancel. So that's all that's left over. And that's good because we can identify this with the current. So dt rho is equal to minus a gradient with respect to x of a current, where the current is given by all this stuff, h bar over 2mi psi star dx psi minus psi dx psi star. That's the current. Why is it a current? Because this has the form of a continuity equation. It's the equation that a quantity satisfies when it's conserved. And probability is certainly conserved. You know, the probability of observing the particles conserved are always sums to 1 or integrates to 1 for this density. And this is a continuity. It tells you that, well, it tells you the following, that the generalization of this to 3 dimensions and so on is this, that the change in time of a density is equal to the divergence of a current. Of course, in 1 dimension is just a single derivative like this. But you see, what does this mean? It means any change in rho must be completely determined by the flux of rho in and out of some volume in your space. So the other way of thinking about this is the following. We can look at the change in time. This is a kind of way to think about this. So we're going to look at the change in time of the integral of some density over some test volume, some little ball in space. We're going to look at that. And what do we know? So this has to be equal to, get rid of the rest of this. So what does this have to? This has to be equal to the integral of, so, and let's put back the time dependence. Right, this is a time dependent thing. Remember, this is rho here is a function of x and t. So let's put that back. So we have this. that has to be equal to that, because the only time dependence is just in the time dependence of rho. It's, there's no time dependence in this R. So that's true. And what is this thing? This has to be, if we look at rho inside this volume, you can think about it as like a mass of fluid or something. The only way the amount of mass in there can change is if there's any fluxes, right, that go in and out of this little volume from the surface of it, from the boundary. Because if this is a conserved quantity, then there are no sources of rho or sinks of rho inside that volume. The only way rho can change in time is if something comes in or something comes out from the outside of this volume you're integrating over. So for any conserved quantity, this has to be minus the integral of j dot ds, where this is a current and this is a little surface element of S. So this is a little surface element that's coming out. And we're going to say that if j dot ds is positive, then you have stuff leaving, right? Because then the current's coming out, it's outside of the little volume, and stuff is going out, so rho is going down. So there's this minus sign. And now you can use the divergence theorem, which you should remember from E&M or what have you. This must be equal to minus the integral over the volume that the surface is covering. So this is the integral over the surface area. Must be equal to the integral over the volume of the divergence of J. And now we look at this here. This was for an arbitrary volume, right? So it doesn't matter what we choose for the volume. It could be arbitrarily small. We could shrink it down to almost a point. And so the only way this would work, the only way this could be equal to that is if the stuff in here is equal. If this stuff is equal. And so we recover this kind of equation. Any conserved quantity has to obey this continuity equation. And we just derived from Schrodinger evolution that the probability density is such a conserved quantity. It's a conserved quantity. Probability isn't created or destroyed in any region of space where a particle might live. The only way probability is created or destroyed is if particles come in or out of that volume, or the probability density associated with the particle. And so there you go. We derived from the Schrodinger equation that has to obey this continuity equation. So that's an important concept. And so when we do things like look at what happens at boundaries or at certain points in your problem, you have to make sure that the probability current is conserved, that any current that's that you match currents. So that if you have a current coming in this way at one point, it has to be the same current that's coming out of the other end if you have some boundary or something like that. So that'll be important later. But this is something you likely would have seen in an undergraduate course, this expression for this J. But I wanted to, hopefully this gives you a sense of where it comes from and why it's defined the way it is. It's just what it has to be given Schrodinger's equation. Okay, so let's do a short example of, let's do a little example of a probability current. Let's look at a plane wave. Let's look at the wave function that's not in our space, but it's the wave function associated with an eigenstate of momentum, this e to the I px over h bar. And from this, we can just calculate what J has to be using this formula. J has to be, incidentally, look at this. This is you can rewrite this actually as the real part of h bar over im psi star dx psi. That's convenient because, well, see, the real part is 1/2 times the number plus its complex conjugate. So this is 1/2, this is the half, this is the number, h bar over mi, this guy. And when you add the complex conjugate, this I becomes minus I, so you get this minus sign. These two exchange, so you get this. This is convenient because it's easier to take a real part of something, typically, than have to compute both of these terms. So let's plug in this solution. It's h bar over im a star e to the minus ipx over h bar. And you take a derivative, it pulls down a factor of ip over h bar. And we have a e to the ipx over h bar. These guys cancel. This I cancels, this h bar cancels, and you get the magnitude of a squared times p over m. And what's p over m? Momentum is mass times velocity, so this is a squared times the velocity. So it's a probability magnitude, a squared, the amplitude squared, times the velocity associated with this momentum p. So this will be important. J will be important when we look at matching boundary conditions. And this is just an example of what it is for a plane wave. So, okay, so now we're set up and we can do what we wanted, which I erased it here, I shouldn't have, but we're now set up to solve this equation. Let me bring it back here. Right, we now want to solve this equation. We want to solve this equation for various potentials V. And what we're going to start with is just simple potentials that are constant almost everywhere except for certain places where the potential will jump. So that's the next piece. So let's think about it. Let's do. So what are we solving? Let me rewrite it in a more convenient way. It's two derivatives plus 2m over h bar squared of e, a constant, minus vx. This whole thing multiplied by psi of x has to be equal to 0. We're going to solve this thing for different potentials v of x. So we're going to look at various v's of x, and they're all going to, for now, look something like this. There will be flat pieces and then some jumps like that. It will be flat, and it will instantly jump at certain values. And then what we want to do is we want to figure out the solutions to this thing for various total energies, E. And we could put, the energy somewhere and conveniently sort of draw a line of where it is. And you see what happens is if V is bigger than E, then this thing is negative for those positions. And if E is bigger than V, then this is positive. And that'll give you different solutions, different kinds of solutions to the Schrödinger equation. But for now, suppose we look at one of these jumps. We also want to know what happens at these jumps. across which your potential jumps from one value to another. And in particular, what we want to do is look at what happens to the derivative of psi of x, just to be sure nothing funny is happening. So we want to look at the derivative of the wave function before and after the jump. So if we do that, then the difference here, this is the difference of this derivative of psi before and after and minus before the jump. But we know from the fundamental theorem of calculus that this must be the integral in going across this jump of the second derivative of psi. Right? Because the integral kills one of these derivatives, so you get the value of the function at the upper interval minus the lower interval. But we know what this is. This is just from Schrodinger equation. X naught plus epsilon, x naught minus epsilon of dx 2m over h bar squared and look at this. If this is a finite number, if Vx only jumps a finite amount, then this is just some number. And this integral, if we make epsilon go to 0, this integral becomes narrow, more and more narrow, and so you just integrate some constant over a very, very narrow interval. So this becomes, approximately equal to 2m over h bar squared times the jump in the velocity times the distance. So an integral is an area, right? So it's this function, the value of this, times the interval which you're integrating, which is 2 epsilon. So this thing, if this is finite, this just goes to 0. And what this means is that the derivative is continuous for finite jumps. So for finite jumps, we have the following boundary conditions. We have that, well, first of all, psi of x should be continuous. It shouldn't jump as we go across one of these steps, and also the derivative shouldn't jump. So that's just true for these jumps. And so that's the proof for the first derivative, that it can't jump if v doesn't go off to infinity or something. Okay, so that's good. And we're gonna do a simple example first of just a single step. So let's do a single step. Well, before I do that, let me just say some general things. So generally, if we were to solve this equation for such stepped functions, then we know that anywhere we look, v is going to be a constant. It has these jumps, but otherwise it's a constant everywhere. So the equation up there has this form in general. Where nu is e minus v. And you can solve this immediately. It's something that we take two derivatives of a function, you get back out the same function times some factor, some constant factor. So there's a solution, and there's two derivatives, so that means you'll get two unknowns. So there's two solutions to this. or you get 2 degrees of freedom. So there's going to be some coefficient a of e to the I square root of 2m nu times x over h bar plus b e to the minus I square root of 2m nu h bar times x. This is the general solution. So if nu is positive, if e is bigger than v, these give you oscillations, right? Because it's e to the I x plus e to the minus ix. If nu is bigger than 0, you get oscillations, right? And if nu is less than 0, what do you get? Well, if nu is less than 0, this becomes a negative number in the square root, so you get another factor of I, which cancels this one out here, so you get exponentials. You get I times I, you get minus something, and here you get plus something. You get exponentials. And those are really the only 2 options, and for most of the problems you do in undergraduates, just looking at these 2 cases and just seeing what happens in these particular cases. So that's the general thing. So let's just do a step. Let's suppose v of x is some v naught times theta of x, which here it's the Heaviside step function. So psi of x is 1 for x bigger than 0 and 0 for x less than or equal to 0. So just go 0 to 1. It's a step. So v of x, this is 0. This is x, v of x. It just goes from 0 to some v naught. Like that. And it does that at 0. And let's pick an energy for this. So we'll suppose E is somewhere here. E is less than V0. So what do we expect? Well, we expect here to get oscillations, and over here to get exponentials. And then we're going to have to use sort of physical intuition to figure out what we should pick for these values. And then we also have this jump that we have to think about. So what do we do? When you have a problem like this, you want to break it up into pieces where there's stuff before the jump and stuff after the jump, because the value of nu changes as you go across this jump. So what do we do? We say that over here, in this region, so there's 2 regions, region 1 and region 2. In region 1, we have oscillations. So we'll have psi of x is equal to a to the e I k x plus b to the e minus I k x, where k is just square root of 2m e over h bar. That's what it is here, because here v is 0, so nu is e, so this is k. Square root of 2m e over h bar, kx. Now, what does this mean? If you think about it, remember when we were looking at positions and momenta, we argued that this guy, even though it's not a normalizable function, you can't square integrate it, it corresponds to an eigenket of momentum. Right? We argued that there's a correspondence between p and the following pseudo eigenvector, e to the I px over h bar. We have this correspondence. So what does this mean? It means that we can interpret these 2 functions as associated with particles moving either in the positive x direction or the negative x direction. And of course, we know that can't possibly be right mathematically because, again, these are not square integrable functions, and to do it properly you have to think about wave packets, which we will in class. But for now, we're just going to sort of sweep that under the rug a little bit and use physics intuition to make sense of this solution. So what does this solution say? It says over here, what do we have? There's no potential. You have some energy. So your energy is just a kinetic energy. It must be just a particle in one dimension just moving along, either in the plus x direction or the minus x direction with some momentum. And that's what these things are. It's a superposition between particles moving plus x and minus x. So, so what do we expect? Well, we expect then for what to happen. We expect particles that come in from over here with this energy to approach this jump in the potential, and this acts like a kind of potential barrier. So there's some incoming particles associated with this term. This is the incoming guys. That come in, and then something happens with this potential, and some of them get reflected back, and those must be the ones going that way. So this is the sort of outgoing guys. And okay, so we have that. And what happens in region 2? Well, in region 2, we know that we have exponentials because E is smaller than V naught. So what does that mean? Well, it means psi of x is equal to some other coefficient, c e to the minus kappa x plus d e to the plus kappa x, where kappa is a number that's square root of 2m v naught minus e over h bar. That's just this amount here. This is, so v naught, e is less than v naught, so this is a positive number. I factored out that factor of I and canceled it with this I to get a minus sign here and plus sign there, so you get these two things. So what do we do? So we look over here, what happens here? We look far away for large x. For large x, this term is a problem. It blows up, right? It's an exponentially blowing up solution. So this can't be physical because our wave function then wouldn't be square integrable or any. We couldn't make any sense of it. We can't even interpret it as an outgoing particle because it's not associated with this kind of function that oscillates. This thing is really an unphysical component of the solution, so that has to be 0. So we're left with this general form. And so now again, it's this combination of mathematics and physical intuition that tells us, well, that A is the incoming part, and we could set things up. We could set up incoming particles through setting up some source of particles over here to shoot at this potential barrier, such that the amplitude, this A, is equal to 1. We can do that. We just have some freedom of choice related to that. So, I mean, if you wanted to do this properly, what would you do? You would probably consider a wave packet corresponding to some particle that you shoot off in this direction. And then, so we'll talk about that. And then this problem you would think about it in terms of the full time-dependent Schrodinger equation. You would ask how the wave packet comes in and what it does when it encounters the potential step. But we don't have that luxury, so we just we use physical intuition to interpret these solutions. So we set magnitude of A is equal to 1. In particular, you could just set A is equal to 1. So we have an incoming particle, which we can think about as sort of in this pseudo-eigenvector state of a definite momentum. It encounters this step, and now we have to apply boundary conditions to figure out what happens here. So when we do that, sort of don't need this anymore. So what do? We have to do boundary conditions at x is equal to 0. So first we have continuity. So psi of 0 has to be continuous. So that means psi of 0 from over here, which is going to be a is 1, it's e to the 0, plus b, has to equal this guy, which is c. So we have 1 plus b is equal to c. And then we also have to have the derivative of psi has to be continuous. And often it's convenient to study not this, but actually the derivative divided by the function itself. That has to be continuous too. And that's also equal to the derivative of the log of psi, just by the chain rule. So that should be also continuous. And that's a convenient thing to study this logarithmic derivative because it cancels some of these exponential bits. So if we look over here, this function, if we take a derivative, we bring down a factor of minus kappa. So this becomes minus kappa minus kappa times c, this guy, right, c e to the minus kappa times at 0. And if we divide by the function, we just get this. So these parts cancel, it's convenient. So this is just minus kappa. And over here, with this guy, we pull down a factor of ik. When we take the derivative, this pulls down ik, this pulls down to minus ik. So we get an a minus b type of deal, times the exponential parts, which is 0. And we divide through by just this function evaluated at x equals 0, which is a plus b, or like this. And we already set a is equal to 1, so you have 1 and 1. Okay. And what do we get from this? We now have two equations. This is k, this is kappa. So we have two equations, this guy and this guy. And we have two unknowns, b and c. So we can just solve that. We can take these two equations, just do some basic algebra. And what do we get? We get that b is equal to minus kappa plus ik over kappa minus ik. And this thing, c, is minus 2ik over kappa minus ik. So these are k's, ik's over here, and these are kappas. And this is our solution to the problem. So what does it mean? It means that, well, let's look at this. We can try to figure out what the amplitude is associated with the outgoing bit. Okay, so what do we know? We know that this part is an exponential decay. So the wave function, let me draw it, I guess. So the wave function, there's an oscillatory part that comes in. Just put it over here. There is an oscillatory part that comes in. And here it becomes exponentially decaying to 0. And there's an associated part that comes out, which is the b part. Out, and then there's an a equals 1 that comes in. And B is, just to remind you from the previous board, it's minus kappa plus ik, kappa minus ik. But look at this. If we calculate B times B star, which is the magnitude of B squared, what do we get? We get this times its complex conjugate, which is k minus ik, k plus ik, kappa plus ik, times the original thing. So the complex conjugate times the original thing, the minuses cancel. And this cancels that, these cancel. So this is 1. So, and that's equal to A. So what does this mean? It means a particle comes in, it encounters this barrier, there's some penetration of the particle into the barrier, and that's this exponential decay. And that's kind of like an evanescent wave in optics, if you're familiar. So there's some chance of observing the particle inside this classically forbidden region, where classically a particle wouldn't be able to go. But then it goes in here a little bit, and then it comes out, because the amplitude of the outgoing portion of the solution, the B, is equal to A. So it's just physically, this is the quantum mechanical version of throwing a particle at a wall and then having the particle come back. Now, it's not an infinite potential barrier, it's just a finite potential barrier, so the particle actually penetrates a little bit into the classically forbidden region. What would happen classically? Classically, this would be your kinetic energy, and as soon as your particle hits here, it'll just recoil back and go back instantaneously. But in quantum mechanics, you have this penetration, which leads to things like tunneling, and so on. And we can see that through the exponential solution portion of the solution. So that's what happens when E is sort of less than the barrier. We can also look at what happens when E is greater than the barrier. Say you had your step potential, but suppose your E was like this. You have your potential, but then your energy, suppose, is higher over there, like that. Then you'd expect the whole thing to be transmitted. So what do we expect? We expect oscillations over here and more oscillations over there. Remember, when E is bigger than V, you get oscillations. If it's less than V, then you get exponentials. That's the kind of rule of thumb. And so what would you get then? Well, then you have to define, instead of kappa over here, you have another K, which is K prime in this region 2. And this K prime is square root of 2m E minus V naught over H bar. And then you have your solutions. And now you have to do some physical intuition arguments for this as well. What's going on over here? Here, we don't expect to have any sources of particles. We're imagining shooting off a particle in this direction, having it come in here. So maybe sometimes it'll be reflected a little bit in the other direction. So we have A and B here, not equal to 0, just as before, just like these A's and B's. But here, we just expect some particles to come out, and we don't expect any particles coming in from over here. So similarly, you have D equals 0 over there. Because, and so then over here in region 2, so let me just, in region 2, we would have, region 1 is the same as before, but in region 2 you would have the following. You'd have C e to the I k prime of x. It's an oscillating guy, and this guy is analogous to a particle with a positive momentum going in this direction. It's like a pseudo-eigenvector of a fixed momentum in the positive x direction. And there's no d because we don't want any particles coming in from over there. So before, when this energy was lower, we threw out the d solution because it was blowing up exponentially, so it's not normalizable. Now, we're using physical intuition and saying we shouldn't have any sources of particles coming from positive infinity. Only have some particles coming in from over here. So this is the physical solution. And then you could go through this whole process again of matching the function at 0. and you'll find 1 plus b is equal to c again. And again, we're setting a equal to 1, just like we did over there. But you would find a slightly different equation for k prime. You would find the following: ik 1 minus b over 1 plus b. This is from the continuity of the. So again, there's always two things you have to check. That psi of x is continuous at x equals 0. That gives you this equation. And then the other one is that the derivative of psi divided by psi at x equals 0 is continuous. Check these two things, get these two equations, and solve for b and c. And what do you get? For b, you get k minus k prime over k plus k prime, and for c you get 2k over k plus k prime. Right? And so what can we learn about this? This, the b, remember, is associated with the oscillations going in this direction, so momentum moving this way. And c is associated with stuff that gets transmitted. So there's going to be a you have an incoming wave of, shoot a particle in this direction. There's going to be some portion of it, sometimes it will get transmitted, and sometimes it will get reflected. And so there's a conservation of probability flux, because we know that whatever probability flux comes in, either it gets reflected or it gets transmitted. We saw in this problem all of it gets reflected, but here some of it gets transmitted, and so we have to do the probability flux analysis. And what's the probability flux tell us? It tells us that a squared, this is the incoming flux, and remember this is h bar k over m. This is that probability current, that's the incoming current. Because we know over here the particle comes in with e to the I kx. And this is h bar k is just the momentum, so this is a squared p over m, a squared times the velocity. The incoming probability flux has to be equal to the sum here of the reflected part, which is h bar k over m, plus the transmitted part. And here it has a different momentum, a different velocity. And that's important because here we'll have h bar k prime over m. Because it picks up some potential energy as it goes over here, and the kinetic energy becomes smaller. So there's a slower flux this way. And it's these fluxes that have to balance. So you solve for these things, and this is the physical interpretation. You have an incoming probability flux. It gets separated out into two things, an outgoing, a reflected part, and a transmitted part. And they have to balance in this way. And so then there's a reflection probability. What's the reflection probability? Well, it's the portion of the incoming flux that comes back to you. So it's this guy divided by this guy, and these h bar k's, are the same. So you just get b squared over a squared, and that's k minus k prime over k plus k prime squared. And what's the transmitted part? The probability you get transmitted, well, it's one or the other. You either reflect it back or you transmit. There's no other option. The particle doesn't get absorbed anywhere. Its probability is conserved. So this must be 1 minus the probability that you get reflected. So you can work that out. But it's also equal to the transmitted part divided by this flux. And that is c squared k prime over a squared k. And this is why it's important to think about this probability current, because that's the one that ensures conservation of probability when you do this kind of physical analysis. It's because we want to make sure that the reflection probability plus the transmission probability is equal to 1. They sum to 1. And so when you think about what that means in terms of balancing fluxes, it has to be these quantities, the magnitude of the probability amplitude squared times the velocity associated with the particle motion in that region. So it has to balance this way, and you can check all this works. You can solve for these these coefficients. This is what you get for the reflection probability. It's just as b squared. And for the transmission, you get 1 minus the reflection coefficient, which is also equal to c squared k prime. Oh, so you might not have seen. So let me rewrite it. So what we found is that the reflection coefficient is b squared over a squared, which is k minus k prime over k plus k prime squared. And the transmission coefficient is the transmitted part, k prime. This is important because that's the velocity. This is the probability current that is conserved. This is c squared k prime over a squared k. And here, if you want, these are both k's, so those cancel. And that's equal to 1 minus r. And that's also equal to 4k k prime over k plus k prime squared. So everything should make sense. If you shoot a particle at some potential guy and your energy is above the potential step, then some part gets transmitted and sometimes the particle gets reflected. And the reflection probability is equal to the probability flux of the reflected part divided by the probability flux of the incoming part. Same thing for the transmission part. Outgoing probability flux divided by incoming probability flux. And that has to sum to 1 because probability is conserved. The probability of transmission has to be equal to 1 minus r, probability of reflection. And so it all works out. And that's basically it. That's the analysis of of what happens when you shoot a particle at a potential barrier. Either you're below the potential step, then particles just get reflected off this barrier, but there's some exponential penetration, like an evanescent wave. If your energy is above the potential step, then incoming particles either get transmitted with some probability given by this, or they get reflected with some probability given by that. And look at this also makes sense. If the potential step is 0, then k prime here is just going to be, this is 0, then k prime is equal to k, and this vanishes, so then the whole thing gets transmitted. So it makes some physical sense. Yeah, so that covers the potential step. And the next thing we're going to do is the infinite well, which instead of dealing with these pseudo-eigenstates associated with particles moving in one direction or the other, which are not normalizable wave functions and are not part of our original Hilbert space, but we can still interpret them in this physical fashion. When we do an infinite well, we'll get actually true states that are in our Hilbert space, and so it'll be easier. But if you wanted to do this in a physical fashion, what would you do? You would really take this particle reflection and transmission seriously, and you would package the particle in a wave packet and see how a wave packet then collides with this potential step. And we'll talk more about wave packets in class. This time, instead of looking at what happens to a single potential step, we're going to look at what happens in an infinite potential well. So we're again solving for stationary states. We're solving the time-independent Schrodinger equation, which has this form for a particular potential. And the potential we'll be interested in is something that looks like, well, here, we're going to go from 0. We're going to go from 0 to A. And from 0 to A, we're going to have no potential. It's going to be 0. And as soon as we hit 0 or A, this thing will shoot off to infinity. like that. So whatever energy we fix in there, we're going to have the energy be bigger than what's going on in here. So what about here in these regions? Well, if V is blowing up to infinity, then really the only way this can work is if psi is equal to 0. There's no other solutions. We can't have exponential decays in here or anything because this is infinity. So infinity times anything, any exponential decay, whatever, it's not going to be 0. So in this special case of an infinite square well, where your potential, you're confining your particle in this interval with very rigid walls that can't penetrate, then psi is equal to 0 out here. And so now we have to figure out what's going on in this region. And again, we're going to have some energies in here. And we know that, the intuition from last time, E is bigger than V, so we get oscillations, right? And so what do we expect in here? In here we expect to get psi of x is a to the e ikx plus b e to the minus ikx. Now it's convenient to, and these are complex numbers, and we have to make psi continuous by forcing it to 0 at these 2 points at 0 and a. And it's convenient for things like this to notice the following, that sine of x you can write as, it's a very important formula to remember. It's e to the ix minus e to the minus ix over 2I, and cosine of x is equal to e to the ix plus e to the minus ix over 2. So in fact, you could rewrite this if you wanted. You could redefine your coefficients so that you still have 2 degrees of freedom, but now your so these are still 2 complex numbers, but now your 2 solutions are sine and cosine. And, well, what do we know? We know that the solution has to vanish out here in these regions. So the function has to go to 0 at these 2 points. And these are oscillatory functions, right? And so the only way that this can work is if you have certain values of k. Right, that's the only way, and k, by the way, is just the usual thing, square root of 2me over h bar. So, solutions to this problem, in the case where you have these special boundary conditions at 0 into a that psi has to vanish, you only get certain solutions for particular values of k. And those values of k are such that the wave, the oscillations that sit in here, can fit inside this box. And so the solution to this, using the boundary conditions, is given by psi of x equal to a sine of kx, where k can only take on certain values that are given by pi n plus 1 over a, where n is 0, 1, 2, and so on. So what do these look like? And a is just some amplitude. Well, they just look like sine waves that sit in here. You can fit half a sine wave That's n equals 0. You can fit in you can fit in a full sine wave like this and so on. So this is n is equal to 0, n is equal to 1. You get these solutions. And this is the only way this can work, that we have the function completely vanish out here. And what does this mean? It means that instead of being able to set our energy wherever we want, remember our energy is related to the k's, we only get certain values of the energy that work. It means that the energies are quantized, and they're given by h bar squared, kn squared over 2m. That's just inverting this equation. And that's equal to h bar squared pi squared 2ma squared m plus 1 squared. Those are the quantized energy levels. So how do we set this A? Well, now this is a proper element of our L2 space. This guy really, it lives in L2R. It's square integrable, and we can normalize it. So A is set by ensuring that psi of x squared dx is equal to 1. And if you do that, if you plug in the sine squared, you'll get a solution for A has to be equal to the square root of 2 over A. So that gives us our wave functions. You see, so how do we know that that's true? Well, because look at what happened here. Remember what we're doing. We're looking for eigenstates of the H operator, which is the Hamiltonian, which is the energy emission operator. Remember what we know about the decomposition theorem. You either get a continuous spectrum or you get a discrete spectrum, or both, And the discrete part of the spectrum, that's the part that has real eigenvectors in your space. So look, this is discrete. You have discrete values of E that these states can be, and that automatically means that your psi's live in your Hilbert space. So they're square integrable, and everything is great. You can normalize them and set up their normalization. So there's a set of eigenfunctions that are given by square root of 2 over A times sine of these kn's pi over A n plus 1 x. And they have their associated eigenvalues. Well, I'm not going to write them again. So here they are, your eigenvectors and your eigenvalues. And they're in your Hilbert space. So this is very different from what we did just a little bit ago when we looked at particles hitting a potential barrier. There we had to be careful because our energies were continuous. It was a free particle, it could have any arbitrary momentum, any kinetic energy it wants. It was moving in one direction, reflecting off a barrier with any energy. In that case, we had a continuous spectrum, and our states were these plane waves, which are not really part of our Hilbert space, so you can't normalize them. But now, in this situation, because of the boundary conditions here, and forcing the wave function to be to 0, that picks out a discrete set of functions that can obey this time-independent Schrodinger equation. And this is that set of functions, these sine waves, these guys. And those correspond to discrete values of the energy. That's the discrete spectrum. So these guys are part of your Hilbert space, and they're square integrable. And what's interesting about this is that, remember, you have that completeness relation So now we don't have a continuous part of our spectrum. We just have an infinite number of discrete states. Remember that in principle, you should be able to decompose your identity on your Hilbert space into your discrete spectrum. There's no continuous part. And can you? Yes, you can. Any function on this interval can be written as an infinite sum of a decomposition in these functions, these signs. So, in particular, any psi of x, any psi of x, any psi of x in our L2, any psi of x in our L2 space. And it's a special L2 space because, we're forcing all the functions to vanish outside that interval, so it's really this space. Any function in there you can write as sum over some complex coefficients of these wave functions. You might ask, what about the boundary conditions? We forced it to 0 there. Even without the boundary conditions, you can use enough sine waves to decompose any function in that interval. And this is the sine Fourier transform, if you want. It's the Fourier series, rather. And so you see it makes sense. Why did we go through all that business with the Hilbert space decomposition? It's to really understand what's going on a little bit better when we do these wave mechanics problems. When we have a continuous spectrum for the energy, and they're Hamiltonian, then you have these pseudo-eigenstates like e to the plus or minus ipx, which are related to just free particle motion with some momentum p. Over each point. So that's for a continuous spectrum. But when we have bound states, like in this infinite well, then we have a discrete spectrum, and that gives us an infinite set of discrete values here for the energy, and we can decompose any function like this. And this is just as we would have for a finite dimensional Hilbert space. And so that's important. It's important to keep in mind when you get continuous things, you get these pseudo-eigenstates which are not square normalizable. And when you have a discrete spectrum, then you get a set of functions that you get a set of functions that you can use to expand any function in your Hilbert space. As follows. This is an important point, I think. So what else can we say about this? Eventually we'll do the harmonic oscillator, and there your potential looks like, a big parabola. And there will also be bound states. And now this thing lives on the whole real line. You don't cut off your wave function or anything in this funny fashion. And we'll see that there's going to be a discrete, there'll be eigenfunctions associated with each energy level. And you can actually prove that you can expand any square interval function on the entire real line as an infinite series of the harmonic oscillator eigenfunctions, just as you would expect from the Hilbert space decomposition theorem. But that's for later. So for now, in terms of what you should have seen in undergraduate courses, and what I tried to review a little bit here is basically what happens when you have the time-independent Schrodinger equation in the presence of a potential step, and then seeing what happens when you vary the energy above and below the step, and there our energies were continuous. We could pick any energy we want. It was a continuous spectrum, and that meant the kind of solutions we got were not square integrable. There were these eigenstates of momentum, if you want, associated with a traveling particle. And then the other case of bound states, where sometimes you get, for the infinite well, for instance, the solutions to that is a discrete set of functions, and then we can expand any function we want as an infinite series in these bound states. Of course, you can also have a finite well. You can have a combination of continuous and discrete states. And that's where I will start in class, is looking at the general problem. What's the general problem? The general problem that we'll consider is a potential V of x. And what we're going to do is imagine that nothing happens to the potential, that it's constant outside of some interval. So we'll go from minus a over 2 to a over 2. And over here, it'll just be 0 or something. And out here, it'll just be 0, the potential. And in between, it'll do something. I don't know, it could be some crazy thing. But we'll look at different cases where it's a potential well, a finite well, or a barrier, like a little rectangle. So we'll look at various things in here. We'll look at maybe this kind of thing, or a rectangular well, a finite well. And what's the intuition here? We're again going to have different values of the energy that we can look at. And some of them will be continuous. In the case of sort of a particle moving in these regions, say if you're shooting a particle off from this direction, it could have any kinetic energy. Those kinds of states will be associated with these oscillations, or exponentially decaying solutions. And sometimes we'll get bound states, which correspond to square integrable wave functions that are associated with eigenstates of our energy that are still within the Hilbert space of interest. So hopefully you're getting a sense of this interplay between discrete and continuous, and you can sort of see how physicists are able to kind of use functions like this to understand what's happening physically, even though they're not really proper wave functions, they're not part of the Hilbert space, because they're associated with the continuous part of the spectrum. Yeah, so that's it, and I think the rest we will sort of do in class. And by the way, in case I might have been going a little bit quickly here in solving this, but this follows directly from the boundary condition, because psi at 0 is just b, which has to be 0, and then psi at a, it has to be a sine k, a has to be 0. So if this is non-zero, the only way this can work is if k takes on these values. It's the only option. So hopefully, I think I went a little fast with this jump, but this is how it's just matching the boundary conditions at 0 and a. As soon as you do that, you get discrete values of k, you get a discrete spectrum for the whole thing, and boom, you have a complete basis of functions that you can decompose on this interval. So pretty cool. And again, we'll do the harmonic oscillator later, and the harmonic oscillator is a parabola. It lives, is the potential is defined everywhere, and you'll get a discrete set of functions that can expand any function on the real line, the square integrable real line, any square integrable function on the whole real line. So pretty cool, and it all should make sense in the context of what we talked about for infinite dimensional Hilbert spaces. Continuous spectrum, discrete spectrum. If you have a discrete spectrum, can decompose any state as an infinite series. If you have a continuous spectrum, then you have this other decomposition where you have to integrate. You have these kinds of functions. Your eigenstates are not square integrable functions, but plane waves, or for momentum, for fixed momentum, or delta functions for position eigenstates. So that's it.